Hello. In this video, we're going to introduce some basic concepts in reservoir engineering. We're going to talk about different pressure regimes. We've done the equations, but what's meant by normally pressured, overpressured, and underpressured reservoirs and what that signifies. Then we'll talk a little bit, just putting some numbers together to how much oil or gas we might encounter underground. And then finally, I'm just going to go through the stages of oil production. Okay, so to do this, I'm going to use my whiteboard here. So this is the whiteboard. Okay, so let's just define a few terms. So we did, in one of the previous lectures, we looked at fluid pressures and we used the measurements of fluid pressures underground to determine the locations of the free water level and the free oil level, and then we could estimate the height of the oil column. But one of the things that was there when we did this, which might have been a bit surprising, is we talked about, well, the water is connected all the way to the surface, in which case you might say, well, I know what the water pressure is because the pressure in the water, I don't really need to measure it. It will be atmospheric pressure plus rho WGZ, assuming a constant density of water, where Z is the depth either below the sea surface or the water table. So this is going to be your depth. Okay. Now, there are reservoirs where what you measure, so PW measured, M for measured, okay, and I'm going to call that PWN, is approximately equal to, within your measurement error or uncertainty, this. And that would be called what's known as a normally pressured reservoir. Okay. Now, what a normally pressured reservoir represents is, imagine you're offshore, at the surface of the sea, okay, the water pressure is equal to atmospheric pressure. As you go down with depth, pressure increases as rho GH or rho GZ actually in this equation. And so when you encounter water in the reservoir, if there is a connected pathway of that water all the way to the sea surface, or indeed if we're onshore to the water table, then that's the water pressure that you might expect. So that seems hopefully straightforward. But it's not as straightforward as that, because you do have other possibilities, which I'm now going to talk about. What happens if the pressure that you measure, and this is the water pressure, so M is what you measure, right? The measured pressure, it's the actual pressure you measure in your reservoir, next to your reservoir. What happens if that is greater than the normal pressure? Well, that's obviously a greater pressure, so it's called an overpressured reservoir. So that makes several. Okay, that's obvious that it's overpressured. But why can you have an overpressured reservoir? And there are two reasons. Okay. The first reason would be a reservoir which is formed at great depth. But remember, this is over geological time. So the oil might have moved from the source rock to the reservoir rock tens of millions of years ago. So imagine that over geological time, we form the reservoir at great depth where the pressures are high, and then that reservoir gets sealed. Right? Essentially, all the flow pathways into the reservoir get sealed up. And that could be a precipitation reaction, it could be faulting, and these faults get sealed. So whatever happens, that reservoir is now basically a closed compartment with no flow in or out and no pressure communication. And then over geological time, the surface gets eroded. So now this reservoir is shallower, it's higher up than its pressure would indicate. So for its depth, it appears to have a higher pressure than you'd expect. So that's what you mean by an overpressured reservoir. An overpressured reservoir isn't a reservoir with a high pressure. It is not a reservoir where the oil and gas pressures are higher than the water pressure. That's always the case, and we've described why that's the case. An overpressured reservoir is where the water pressure, and I emphasize the measured water pressure, is higher than you would expect for the column of water. Okay. That's one explanation. The other explanation, and you see this as a good example in the Gulf of Mexico, is when I say, well, for instance, I'm in this room, but I can't see the sky, but I feel atmospheric pressure, that's because there's a continuous pathway of air all the way to the sky. But imagine the building was collapsing on top of it. I'd actually feel a much higher pressure. I'd actually feel the pressure of the roof and the material falling on me. You might say, well, rock isn't collapsing, is it? Well, actually, very slowly, this is what you find. So if we take the Gulf of Mexico, the Mississippi dumping huge amounts of sediment into the Gulf of Mexico, that sand is compressing, and it's compressing slowly, and it's been compressing for millions of years, but it's still under compression. So when you look at the water pressure, now imagine you're deep underground, you've got a column of water, but it's mixed with sand, and the two together are falling down and pressing on you. So in fact, the pressure that you feel is not just from the column of water, there's also contribution from the rock. As I said before, obviously rock is more dense than water. If you take quartz, for instance, it has a density of 2,700 kilograms per cubic meter, so more than 2.5 times that of water. So it's denser, so you see a much higher pressure. Okay, so that's quite normal in sedimentary basins that are still essentially under compaction, right? Still compacted. You can have just obviously you can see this from combinatorics. The measure pressure could be less than the normal pressure, and of course that's under pressure. Okay, so why do you have an under-pressured reservoir? The reason for this, so here you now have a pressure that is lower than you'd expect for depth, and what this means is that where you have a reservoir that's actually formed at quite shallow depth, again gets geologically isolated, and then over geological time there's sediment, more sediment goes on top of it. So now it finds itself to be quite deep, but it still sees the pressure when it was formed or when it was sealed as when it was much shallower. Okay, so if you look at these reservoirs, an under-pressured reservoir is very safe to drill, so that's good. However, the fluid pressures tend to be lower than you'd expect for the depth, so it's not so good for production. For basically, the pressure that will allow the fluids to move out of the reservoir is less than you'd hope. An over-pressured reservoir is much more dangerous when it comes to drilling because you're encountering very high pressures. On the other hand, it's good for production. Okay, so that completes what I wanted to say for the pressure analysis. So I'm going to clear that, and then I'm going to notice the one thing that we showed we could calculate was this H, which was the height of the oil column, the difference between either the two contacts, if you had log measurements, which is actually the more accurate measurement, or between the two free levels. Okay, so you have H. Now, what you do is you use that to calculate the volume of oil that you have underground in your reservoir, and the symbol that we use for it is N. So N, right, is normally called, given this acronym, sounds a bit bizarre. Okay, STOIP stands for stock tank oil initially in place. Okay, so it's rather a long acronym. Don't get worried about the use of the word stock tank. It doesn't mean to say you actually have to measure it in barrels, although traditionally it is. But what it is, it's the volume of oil measured at the surface. So I might have the oil underground, but imagine by some magic process, I can take this all to the surface. We always measure oil volumes as what's at the surface because it's the stuff at the surface that we sell. Okay, so N can be written with the following equation. And I'll just go through this. And then I'm going to define all the terms, and then we're going to go through some examples. Okay, so let's talk about the various terms. So the first term here, V, is called the gross rock volume. So the gross rock volume is, I've got a volume of rock underground that potentially contains oil. Okay. Now, if we have a very simple geometry, okay, that's going to be some cross-sectional area times some height. So if you imagine a sort of pancake geology where the height we've calculated from the pressure analysis and then an area. Now, of course, in general, it's going to be more complex than that, so don't oversimplify it. But the gross rock volume is essentially found from two things. One is either logs or the pressure analysis that gives you the height of the oil column, and then a seismic survey, the sound waves, that give you some idea of the extent of the field. So impermeable rock will surround this field to stop the hydrocarbon escaping. You can normally detect where that impermeable rock is because you get a reflection, sound wave reflection from it. And so that gives you the gross rock volume. Okay. So then let's go through the other terms. This term, this is a phi term, by the way. It's a Greek F, not some other sort of Norwegian symbol or external diameter symbol. So, you know, when you're on Word, don't let Bill Gates tell you what it is. It's a Greek symbol. Phi is the Greek symbol that is used in flow and porous media to represent porosity. And porosity is, okay, you've got this rock, okay, the rock is porous. There is only a fraction of the pore volume that is void space that can contain hydrocarbon, and that's the porosity, okay? So let's actually put some typical values here, and these are just example values so that I can do a calculation, okay? It's not all reservoirs look like this, okay? So let's give an example just for illustrative purposes where we have an oil column height of 30 meters, that's quite high. An area, normally we have an area that extends over several kilometers, so we might have 2 times 2, say 2 kilometers by 2 kilometers, that's 2 times 10 to the 6, and that's going to be square meters. Okay? Porosity here, typical value is about 20%. So if we have a sand pack, just for an example, if you have a sand pack, that may be about 35, maybe as high as 40%. Okay, so also if you have some coffee grounds before the barista sort of bangs things down, that probably has a porosity of about 40%. Once it's banged down, it's about 35%. But of course, this rock is cemented together. The geological processes essentially force the grains together and clog up some of the pore space. So typical porosity around 20%. Lower than about 10%, it's difficult to have fluid flow, and you sort of encounter those low porosities in shales. So let's take this as an example. So this seems to be the pore volume, right? So this is the volume of the pores, but there is another term that we traditionally use, which is called this. This is called net to gross, because we had a gross rock volume. So what is net to gross? Okay. We have this volume of rock. It has an average porosity, and that porosity can be measured both from the log signatures, right, because you look at the overall density, but also from taking a sample of rock to the surface and measuring the porosity. But you may have a reservoir, you know, so with a nice sandstone, but there'll be some clay layers, or there'll be some layers of shale in the middle of the reservoir. So not all of the rock either contains hydrocarbon or contains hydrocarbon that actually can be produced, right, because it's either very low permeability. And so the net to gross is the fraction of the total volume that actually contains rock in which there's going to be some sort of fluid flow. So it sounds rather empirical, but it's actually quite a useful concept. And you can see this while you're drilling. You go through a layer of sand, there's some clay or some shale, then more sand, then you see the contacts, then you might see a continuous low permeability rock that surrounds it. So that's your net to gross. Okay, so let's, again, think of a typical number. Imagine this is quite a good quality reservoir, so let's put 0.8. Okay, SOI is, the next term is the initial oil saturation. Okay, so what is that? So originally, the rock is saturated with water, salty water, saline water, brine is the word. Oil moves in to the rock. It is the non-wetting phase. It doesn't like the surface. It needs a positive pressure, a higher pressure than the water to squeeze into the pore space. So there is always water originally present. So the oil doesn't fill all the pore space. It fills a reasonable fraction of it. 80% is actually quite a high initial oil saturation. And again, that can be inferred from logs, but it can also be inferred from actually taking a sample of the rock saturated with oil and water and taken to the surface. That's actually a little bit more complex for the reasons that's just coming next, but it's something that in principle. So that those four terms together, right? How much rock there is, then times the porosity. So that's the pore space, but not all the pore space allows flow. So you have another fraction, and then not all that pore space contains oil. That would seem to give you the oil volume. But of course, that's the oil volume underground. We need to convert it, conversion essentially, from the reservoir to the surface. So BO, it's a rather odd symbol, and I don't know where that comes from, okay, is the initial. Right? I stands for initial. It's what there is when you first discover the field. When you start doing things with the field and trying to produce the oil, these numbers will change for reasons I'm about to describe, but this is what we have to do. So this is the initial oil formation volume factor. So it's rather a mouthful, and it's just a mouthful. Okay, I don't, these aren't words that are particularly significant. Initial means what you first find when you discover it. Oil is because it's to do with oil. Okay, the formation volume factor is a very long-winded way of saying that it's equivalent to the ratio of the reservoir volume to the surface volume. So you can see this, if I divide by BO, okay, then I've divided by reservoir divided by surface. So actually it converts a reservoir volume into a surface volume. So just look at that. You just have to memorize that BO is defined as the ratio of a reservoir volume to surface volume, right? That's it. And that's something that can be measured in the sense that I can take oil samples out of the reservoir. When I discover it, I take it into a laboratory, I reproduce the high temperatures and pressures that I see deep underground, which I have measured, okay? And then I say, well, I'm going to take it to the surface, and so what happens then? Now you might say, oh yeah, well that's obvious because, okay, the temperatures are slightly high in a reservoir, so as things cool, they tend to shrink, but actually the main thing is the pressure's really high. So you say, okay, the fluid's under really high pressure, it's all squeezed together. When I take it to the surface, the fluids expand. And so the reservoir volume is less than the surface volume, so BO is less than 1. That actually is incorrect. Actually, BO is typically going to be greater than 1. Okay, it's greater than 1, and a typical value I'm going to put in here is, say, 1.6 for quite a light oil. So, how can oil shrink when you drop pressure? It's because of what was described in one of the former slides, but very quickly, is oil is a mixture of hundreds of different chemical components at high pressure. So light components that would be gases at surface conditions, can dissolve in the oil. So this oil, actually, often the principal components chemically are going to be methane, ethane, maybe even CO2. When I take that oil to the surface, those components come out of the oil. What remains as the liquid phase, therefore, shrinks. And this is simply the ratio of volumes of what is liquid. The composition of the liquid, the molecules that are in the liquid are different in the two cases. That's why you have to be careful in that definition. So in fact, what tends to happen is that things shrink. Okay, let's, I gave you an example, so let's actually do a calculation now. Okay. Let's actually work out how much oil we have underground in our little example, right? So we've got 30 times 2 times 2, right? So that's 30 times 4 times 10 to the 6, okay, times 0.2 times net to gross times another 0.8 divided by 1.6. Okay, so let's just do some things here. 0.6, that's going to be a 2 here, right? So that's twice that. That goes there. That's a 0.1. Okay, so let's try and do this carefully. So we've got 0.1 times 30 is going to be 3 times 4, so that's 12. Okay, times 0.8. Okay, times 10 to the 6. Right, let's just check that we got everything there. That's 312 times 0.6. So that's approximately, that's 9.6, isn't it? That's approximately 10 to the 7 cubic meters. Okay, and if we want to do this in barrels, So I said there were about 6 barrels to a cubic meter. So that looks like 6, right, times 10 to the 7. Oops, this looks a bit weird. Times 10 to the 7. Okay, so let's just, there's the calculation. There's nothing terribly exciting or dramatic about that calculation. So we get something that's around 100 million cubic meters. Okay, and we do normally quote oil volumes in standard cubic feet. Okay, sorry, in stock tank barrels. Okay, so just erasing that. That's it. So we normally quote volumes in barrels. Okay, and they're about, every cubic meter is about 6 barrels, and you can do the conversion. This is just an example. Okay. But now let's just look at the way in which it's written, because that's key. Okay. So you notice here, right? If we maybe have a different color here. If we notice, we've written here STB. S stands for stock tank, T for tank, B for barrels. Now, why do we write STB rather than just barrels, or B for barrels? I'll tell you why. Because this is a volume measured at the surface. And petroleum engineering, that's really important. When you quote a volume, you need to say, is it, a cubic meter is a cubic meter, a barrel is a barrel. But was it measured at the surface or in the reservoir? You just have to say it. You can't hedge around, okay? So whenever we quote N, the amount of oil we have, I know it's underground, but we quote it as though it was all taken to the surface. Okay, so stock tank barrels. Okay, just to emphasize that. Now we'll look at the next slightly bizarre thing is, well, what have I done here? What's this MM? Now, in SI units, we know SI, M is mega, and that's 10 to the 6. Unfortunately, when we have field units, okay, M actually stands for mille, right, 1,000. So it is a bit funny because certainly, in the US oil industry, we're not going to use SI, Système International. We're not going to take some French units. We're going to use good old M, meaning a French word, or indeed an Italian word for 1,000. Okay, so that's how it is. Okay, then if you have MM, you say, okay, well, MM, yeah, okay, we get this M, in the Roman number system is 1,000. 2 M's is 2,000. Right, so that's the year 2000. No, in field units, 2 M's together is 1,000 times 1,000. So MM actually means a million. Okay. Now, it sounds a bit silly and it sounds a bit confusing, but actually once you get used to it, you just get used to it, right? So if you see stock tank barrels with MM, you know it's a million. Okay. However, here's a tip. Where people sometimes go wrong is they try and be over clever. So they say, well, I'm going to quote it in cubic meters. So I'm going to do, say, 10 M meters cubed. Don't do that. It's very confusing because what does that M mean? Does it mean 10 to the 6? Or are you actually doing this, it's the oil industry, so they can't do SI properly, so I'm going to sort of stuff in something that isn't quite SI and hope to get away with it, a bit of a compromise. Maybe I won't offend anyone. Well, actually, what you've done is you've just been confusing. Okay, so don't do this. If you're doing it in SI, nothing wrong with SI, do it again, rigorously. You've got a PhD in theoretical physics type SI, all right, times 10 to the 7. Okay, you're going to do it in field units, that's fine. Okay. And then there's no confusion. So that's what we end up with. Now, this looks interesting. 60 million stock tank barrels, by the standards of a major oil company, is considered actually quite a small field. If we looked at those biggest oil fields in the world in a previous lecture, we were looking at billions of barrels, right? Another 3 orders of magnitude or 2 orders of magnitude larger. So most major oil companies would not be interested, particularly in a field of that size. Right? They're looking at the bigger fields, the more complex things. But there's a lot of oil here, just to give you some idea of value, right? At the current oil price, say, of $50 a barrel, right, per stock tank barrel, okay, this is worth 60 times 50, right, $1 million. Okay, and that's $3 billion, right? 6 times 5 is 30, so it's $3 billion. Right. So just to give you some idea of the sort of the value of the work that is done as a reservoir engineer, is this field potentially has 3 billion barrels worth of oil. Okay, as I'm going to show in the next slide, you're lucky if you get half of that oil out. Okay, and as I said, it's a sort of field that large companies wouldn't really work on. If you were, you may be as a junior reservoir engineer working on it for a few months. As a smaller company, you may be devoting some time, but it's certainly, you're not going to spend your whole career working on just that one field, right? It's a project that you may spend a year on. Now, there isn't a magic to reservoir engineering. There's no magic technology that gets all the oil out, but good engineering, as opposed to poor engineering, should make at least a difference, I mean, of a few percent. Let's just say 1% in terms of additional recovery. Well, 1%, right, is $30 million. And that would be, for most engineers, less than a year's work. So the value of what we're doing, the value of understanding this, is enormous. But as I said, there isn't a magic bullet. It's just good engineering, understanding flow processes underground. Okay, so I'll finish this bit here. So I'm going to now clear everything. Okay, and we're going to start again. Okay, maybe with black. And we're just going to now talk about recovery. So we talked about, well, you're lucky if you get half the oil out of the ground. So what actually is going on? So here is a plot. Whoops, that was terrible. So let's get rid of that. Pretty shameful. Let's have another go. Drawing a better straight line, shall we? Okay, so what we have on this axis is time. And this is going to be in years. And what's on this is what's called recovery factor. So recovery factor is the amount of oil I produce, again in stock tank barrels, divided by what I had to begin with, so MP over N. And obviously a recovery factor of 1, that's ideal, right? And so this is going to be about 0.5, right? It's not necessarily drawn accurately to scale. Okay, so now let's look at what can happen. Let's try some different colors, okay? So what you would normally do is you discover a field, okay, and you drill some wells. And as I've just said, the oil is often at high pressure, and it's certainly at higher pressure than the water surrounding it, so that oil will come to the surface naturally. So what you would tend to do is you tend to have rapid production, okay? But the final recovery factor is unlikely to exceed more than about 20%. So we're normally looking at 5 to 20%, and this is called primary production. Now, we're going to talk about primary production, secondary production, tertiary production. Prima, seconda, terza. That's obvious sort of from an Italian concept. It just means first, second, third. In English, sometimes primary means the most important, okay? And then of course, it's the same in any other language. But here it is just a time sequence. So primary is what comes first. What comes second is secondary. What comes third is tertiary. Okay, so primary production is what comes first in the production of an oil field, and it is production, okay, with no injection, right? So you don't inject anything, so the fluid pressure has to decrease, okay? So in primary production, what happens is you're drilling wells, you do not inject any fluid. Fluid is coming out from the subsurface, so the reservoir pressure drops, okay? Sometimes people say it's using the reservoir's own energy, the stored energy of the pressure is pushing the fluids out. But why is the production so low? Well, what happens is you end up with a reservoir that's low pressure and still full of oil, right? You haven't pushed the oil out in any way. And in fact, it's a little bit worse than that because, as we just said, as the reservoir pressure drops, gas comes out of solution. And if this happens within the reservoir, gas flows much more readily than oil. So what happens is the pressure drops, and it drops below a pressure called the bubble point, which we're going to describe in a subsequent lecture. It drops below the bubble point, and you start producing excessive amounts of gas. And then it becomes uneconomic to continue unless you're selling the gas. So what you normally want to do is the time scale here is normally a few years. So maybe make that 1 year, 2 years. After a couple of years, normally, what you want to do is you need to do something else. And what you need to do is you need to maintain the pressure and you need to push the oil out. So we get something that looks like this. And that's called secondary, right? And sometimes the symbol for it is with a little O above there. Typical recovery factors are in the range of about 30 to 60%. Okay. And you inject something, and that something is normally water. Okay, that's why I'm drawing this in blue, but it could be gas. Okay, and what it does is to maintain pressure. And to displace oil. So secondary recovery is fluids coming out of the subsurface. If you inject the same reservoir volume of something else, you're going to maintain pressure. That's just simple material balance, again, a subject that's coming later. So you inject something, and that something is normally water, normally seawater or water from an aquifer, something that's cheap. So what that does is keep the pressure high. So that's good. The second thing it does, and that's a distinct physical effect, is that it also displaces the oil. It pushes the oil out. Okay, it removes the oil from the pore space. So you're pushing it out. And with modern drilling, where you place your injectors in locations to contact as much oil as possible, we can get, in some reservoirs, recovery factors of 50% or even more. But normally, secondary recovery may continue for a period of maybe 20 years, maybe longer in some large Middle Eastern fields, but certainly if it's operated by a Western company and you want to get this sort of return on investment, we're normally looking at timeframes of around 20 years. So how do we get to even higher recovery? We have to do something a bit more exotic. So we can do what's called tertiary recovery, okay? And this time I'm not going to spell it out. And this gets us recovery factors that are normally in the range of 50 to 70%. You never get all the oil out. Oil and water don't mix. So although the water is displacing oil, there's still oil that's basically trapped in the pore space. Tertiary recovery is where you inject another fluid, right? Another fluid which is different from what you had to begin with. And that is to displace, okay, remaining oil. So it gets rid of the remaining oil. And sometimes we see these terms that are used, EUR and IOR. So I'm just going to So sometimes what people do is they say, okay, I've injected water for 20 years. Now what I'm going to do is I'm going to do something that's going to boost the recovery. And we often call this enhanced oil recovery, EOR, or improved oil recovery, IOR. And normally what you're doing there is you're injecting another phase that basically flushes out the oil. So the first thing you can do is you can inject gas. Actually, gas and oil can often mix if we inject CO2, which is a really lovely thing to do because it does mix with the oil. And obviously, it's better than having it released into the atmosphere. So if you inject CO2, that mixes with the oil and essentially cleans out the rock. You can do the same. I mean, if you've got oily hands, what you do, you wash them in soap, so you can inject surfactants. Sometimes what you can do is actually just change the composition of the brine. You make it less salty, and actually that makes the rock more water wet and allows oil that's sort of stuck to the surface. So the surface has got oily. It allows the oil essentially to detach from the surface and be produced. Sometimes what happens is, well, say if you're injecting gas or water, it tends to go along a high permeability region. So you've got this oil over here that's been, quote, bypassed. Whereas if you inject a polymer, then that polymer makes the water viscous and it pushes everything. So there are lots of different things that you can do to improve recovery. The problem with it is simply cost. So if we look at the present oil price is $50 a barrel is 160 litres. That's 30 cents, right? It could be American cents or Euro cents, it's about the same per litre. You can't buy mineral water for that, okay? So oil is astonishingly valuable to our economy, but volume by volume, it's actually really very cheap. Right? So while it's great to inject these wonderful chemicals, it's expensive. The other thing is, what do you make the chemicals out of? Yeah, you make them out of oil. So if the oil price goes up, so does the price of it. So enhanced oil recovery is something, particularly when it comes to CO2, and particularly when it comes to some clever things like simply changing the salinity of the brine. These are things to look at. So that's more or less where I'm going to conclude this lecture. I just want to say one quick thing is, normally this is how you develop an oil field. You do prime production for a year or two, then you start injecting normally water, and then near the end of, quotes, the field life, after about 20 years, you might inject something else, and that's normally an EOR or an IOR scheme. However, strictly speaking, primary, secondary, tertiary are a time sequence: first, second, third. So it's the time, it's when. Okay? EOR and IOR is actually what you're injecting. Okay? It's that I'm injecting something different. And so, in fact, EOR can be applied earlier. Right? There's nothing stopping you, for instance, immediately after primary production, injecting carbon dioxide, low salinity water, surfactant. So that would be a secondary process because it's what you did second, but it will be an EOR or an IOR process. Okay. Similarly, you could do something third that isn't EOR. So one thing people have considered in the North Sea is you've got residual oil. That oil is quite a light oil. It produces quite a lot of gas when you drop the pressure. There is a gas infrastructure. You can sell the gas. It's actually valuable. So why don't you just drop the pressure, stop injecting, drop the pressure and produce the field as a gas field? So that's a tertiary process. It's the third thing you did. First of all, you did primary recovery, then you injected water. Now you're just going to drop the pressure and produce gas. Third thing, but it's certainly not EOR or IOR. The last thing is EOR and IOR, enhanced and improved in English, actually mean the same thing. But enhanced sounds a little bit better, even better than improved. So you normally see EOR used for certainly the more exotic or expensive things such as, for example, CO2 flooding, surfactants. IOR sometimes is used to describe processes a little bit cheaper, like low salinity water flooding, where we remove some of the salt from the brine. Occasionally it's used to describe all sorts of manner of other things that aren't really to do with the production mechanism in the reservoir. And I'm not going to consider that. So things like artificial lift, horizontal drilling, etc. Okay, those are things that will improve recovery, but I'm going to use them strictly in a reservoir engineering context. That is, a piece of rock a long way away from the wells, how have I got that oil out? Okay? So in that sense, I'm sticking with these definitions. So there's a little bit more detail in the notes. However, I'm going to finish the introduction here. So what we will do as we'll continue this series is we'll talk a little bit more actually about the fluid properties and what happens when you inject another phase, what happens when you allow the pressure to drop. But, I will finish there. Thank you.